You ever see a case of mistaken identity? Well, in the world of chemistry, it happens literally all the time. You can have molecules that share the exact same list of ingredients, but they act like complete strangers to each other. So today, we're going to dive into this chemical identity crisis and figure out what's really going on.
Okay, just look at these two molecules. On paper, they have the exact same formula, C4H10. That's 4 carbon atoms and 10 hydrogen atoms. Sounds simple, right? Well, get this. One of them boils at -1 degree Celsius, and the other one boils way down at -11. How is that even possible if they're made of the exact same stuff? That's the puzzle we're here to solve.
And the solution to our mystery has a name: isomers. You can think of isomers as the chemical world's doppelgangers. They have the same molecular formula, the same exact parts list, but the atoms are just put together in a different way. And that different arrangement, well, that's the key. It changes absolutely everything.
All right, so to solve this thing, we need to follow the clues. And our first clue leads us to a group of molecules called structural isomers. The best way to think about these is like they're built from the exact same kit, but they're following completely different blueprints.
With structural isomers, the way the atoms are connected, the actual sequence of who's bonded to whom is totally different. The Lego analogy is seriously perfect for this. Imagine you've got a pile of bricks. You could use those bricks to build a car, or you could use the exact same bricks to build a house. Same parts, totally different structures.
So let's look at a real example. Remember our mystery molecules from the beginning, butane and isobutane? Here they are. Butane is just a straight, simple chain of 4 carbons all in a row. But isobutane, it's got a main chain of 3 carbons with one branching off the middle. They both have that C4H10 formula, but they have a different carbon skeleton. This is what we call a chain isomer.
Now, sometimes the carbon skeleton actually stays the same, but a key group attached to it just moves to a new spot. In propan-1-ol, you see that OH group? It's hanging out on the first carbon. But in propan-2-ol, boom, it's hopped over to the second carbon. The backbone is identical, but the position of that important group has changed, and that, you guessed it, makes them position isomers.
So how can you quickly tell the difference between a chain and a position isomer without staring at it for ages? Well, chemists have this fantastic little trick. They call it the magic number. For butane, the main chain is 4 carbons with 0 branches, so its magic number is 40. For isobutane, the main chain is 3 carbons with a 1 carbon branch. Its magic number is 31. See, the numbers are different, so they have to be chain isomers. It's a really slick and simple way to figure it out.
Okay, now for the most dramatic identity swap of them all, functional isomers. This is where the same set of atoms rearrange themselves to form completely different chemical families. It's wild. For instance, a molecule with the formula C2H6O could be an alcohol, or it could be an ether, which has completely different properties. It's the same formula, but they belong to totally different families of compounds.
So far, we've been looking at molecules with different blueprints, but our second clue is way more subtle. It's not about the connections, it's about the arrangement in 3-dimensional space. And this is where we get to explore the really fascinating world of stereoisomers.
Now, with stereoisomers, the blueprint is the same. Atom A is connected to B, and B is connected to C in both molecules. That part doesn't change. The difference is how those atoms are actually oriented in space. Are they pointing up or down or left or right relative to each other? That's what suddenly matters here.
One type of stereoisomer pops up because of something called restricted rotation. Imagine you have 2 beads connected by a single string. You can spin them around freely, no problem. Now, what if you connect them with 2 strings, like rungs on a ladder? All of a sudden, they're locked in place. That's exactly what a carbon-carbon double bond does. It stops things from spinning around, and that creates what we call geometric isomers.
So this whole locked-in place thing leads to 2 main possibilities. If the important groups are stuck on the same side of that double bond, we call it a cis isomer. A good way to remember this is cis is on the same side. Simple, right? And if they're on opposite sides, it's a trans isomer. Just think transatlantic, like going across the ocean.
But what happens if there isn't a double bond? Then we might be dealing with optical isomers. And the secret here is something called a chiral carbon. That's a fancy term for a carbon atom that's bonded to 4 completely different things. When that happens, the molecule gets what we call handedness. Just look at your own hands. They're mirror images of each other, but they're not identical, are they?
And that right there is the defining feature of these optical isomers. They are perfect mirror images, but you can't stack one perfectly on top of the other. The official term for this, the one chemists use, is non-superimposable mirror images.
Let me make this crystal clear. Think about your left hand. Its perfect mirror image is, of course, your right hand. But try to place them on top of each other, palm to palm. They don't line up, do they? Your thumbs point in opposite directions. They just don't match up. That is what non-superimposable means, and it is the absolute key to understanding these molecules.
Okay, so we've got chain, position, functional, geometric, and optical isomers. That's a lot to keep track of. But what happens if a molecule could be classified as more than one type? How do chemists decide which label to use? Well, this brings us to the big reveal, the chemist's priority rules.
To avoid any confusion and make sure everyone's on the same page, chemists have an established hierarchy, a priority list. So if you have two molecules that could be seen as both a functional isomer and a chain isomer, for example, you'd look at the list. Functional is higher up, so that's what you'd call it. This system ensures every chemist in the world is speaking the exact same language.
And that's really the crucial point here. Once you understand all the different types of isomers and you have this priority list to handle any weird overlaps, you can solve this chemical identity crisis every single time. It's a beautiful system of pure logic.
And trust me, this is not just some academic puzzle. It has profound, real-world consequences. So I'm going to leave you with this question. If a drug molecule has one of those chiral centers, giving it a left-handed and a right-handed version, is it possible that one of those mirror images could be a lifesaver while the other is completely useless, or even worse, dangerous? The answer is a chilling yes, and it's exactly why understanding isomers can literally be a matter of life and death.